So today's sea level rise talk will be given by Pierre Dutrieux. Pierre has a PhD in ocean physics from the University of Hawaii. Following his PhD on, he did his PhD, sorry, on tropical ocean circulation and dynamics. Following this, he directed his attention towards ice-ocean interaction with polar ice sheets. He first working at British Antarctic Survey in Cambridge. He then worked for a little while at the University of Washington before becoming an assistant research professor at Lamont Doherty Earth Observatory.
Yes, thank you very much. Thanks, Greg, for the opportunity to come here and talk to you, and hopefully that's the beginning of interesting discussions between us. And so this is, the subject of this study. I'm sure you've seen a lot of pictures, in this seminar series, ice sheet and ocean. But this is an ice shelf, so floating, the extension of the ice sheet, floating extension over the ocean. And so that's the subject of this talk, how the ocean and the ice interact, the processes that arise as they do. And I'm going to expressly really focus this talk on large melting cases. So, but I'll cover basic processes as I go. And that is not working. So I'm sharing my screen, but I can't. Oh, well, okay, I can click. Good. So you probably have seen many about every 3 months there's a new paper in Nature Geoscience coming up talking about sea level rise, and so it's either coming from Antarctica or it's coming from Greenland, and sometimes there are contrasting views. Sometimes the ocean is contributing to increasing sea level, and sometimes the ocean is going to not lead to such a strong sea level rise as one might expect. So depending, if the ocean is warm or cold, or if it varies. And so here, this graphic you've seen many times. It shows the contributions to global sea level rise arising from Antarctica, and it discretizes it in terms of what is the contribution coming from East Antarctica in yellow. And so it's roughly a gain in mass in Antarctica, in East Antarctica. And on the peninsula, it's roughly 0 to a small loss. And the big loss, which leads to the big loss overall in Antarctica, arises from the West Antarctic sector up to now, over the observational record. And this is going into the future. These are the projections from the IPCC. And this is just to show that this is the projection that the IPCC had, and this is what we have observed. So that was these projections were made in 2006, and this is what we have observed since. So if anything, we are on the high range of the projection. Okay, so that is a movie that doesn't work. But
was projections 2013, the IPCC 2013, or?
Yes, 2013. So it's a range projection. So the range is between 10 centimeters to 2 meters. And basically the issue here that we're concerned with is the uncertainty, which basically completely arises from this West Antarctic sector. So ice sheet is, as you know, is not an immovable white giant. It reacts dynamically to forcing, and forcing arises from the atmosphere and the ocean. But the fact that West Antarctica is unstable and susceptible to instability is a very, very old idea. And the main gist of it is that most of West Antarctica is sitting way below sea level. And so it basically is bathing into waters. And so if these waters are warm enough, they can melt the ice shelf. And they can remove the friction at the base of the ice, and that's the main factor for the interaction. And so you can think of the ice shelf as being the buttresses, like cathedrals. They buttress the flow of ice coming from upstream. So in general, we have a balance between accumulation on the continent, which basically grows the ice sheet, and then the ice flows under its own weight viscously towards the coast. And at some point, it's thin enough that it comes afloat, forming a cavity. And so the interaction in Antarctica between the ocean and the ice sheet is at the guiding front and in this cavity. And so if you have a balance between the ice outflows and the accumulation, you don't lose any ice. Right now we have an imbalance where we have more ice coming out in West Antarctica that is being replaced by accumulation. And here in this diagram, I'm basically talking about, this illustrates an idea that was developed by Schuf in 2007, which is that of the Marina Instability. And that is, if you're on a retrobed slope, if you start grinding at the ice by melting, you are basically exposing thicker and thicker columns of ice to the ocean. And so if you have a thicker column of ice, you accelerate the flow of ice because ice flow is driven by gravity. And so if you accelerate the flow of ice, you stretch it, and so you thin even more, and so you expose even more, and so that's a positive feedback loop that is going to accelerate the flow of ice continuously. But don't forget, this goes the other direction as well. If you, for some reason, you stop, you don't melt as much, so you reground. Now you go into thinner columns, so you decelerate, and so you thicken even more, and so that's the feedback goes in both ways. So it's unstable in both directions. Okay, so what does the observational record show over 20 years and now extended over 25 years? If we look at the ice sheet has been accelerating in this sector. So that's what this diagram shows. The velocities in color here, and the areas where we have the big red circles have been losing ice extensively, contributing to around 10% to global sea level right now rise. And here I'm showing in this paper they looked at the thickness of the ice, well actually the surface elevation of the ice from satellite altimeters, the ice shelves in color, and the areas that are red have been thinning, and so the ice shelf have been thinning, and this buttressing has been removed, and the areas that are blue have been thickening, and so all of this sector have been thinning extensively. And so now we have this dynamic feedback that I was talking about. We have thinning, which allows for the ice to flow faster into the ocean. And this thinning is driven by the presence of warm water. So here in this panel I'm showing the temperature of the water on the continental shelf, and so pretty much all around Antarctica what we tend to have are freezing cold water, near freezing cold waters, except in this sector where we have warm water that is available offshore that goes on the continental shelves and is available to melt the ice extensively in this sector. So before maybe going into the processes that lead to this interaction between the ice and the ocean in this warm case scenario, I just wanted to point out, other interesting bits of, process that matter for the global climate. One is that these areas are also sectors for deep water formation. So in these sectors where we have near freezing, the ice-ocean interaction, these areas are just there's some deep water that was formed by brine rejection, so they are highly saline water. Yes, a question, right?
Yeah, for the temperature.
Yes.
What's the temperature? It's the annual mean temperature or the annual maximum? I mean, summer temperature?
It's based on CTD, so it's summer CTD observations.
Summer sort of maximum.
Summer climatology.
December, January.
January to December to March in general.
Okay.
And depending on sectors, it's variable. In this sector, it's actually at the bottom of at the bottom it's not that variable. In the upper part of the water column, it's highly seasonally variable and internally variable.
Yes.
Yeah.
Yeah, but at the bottom it is minus.
So here it's -2. Here it's 1.5.
Yes.
And here it's -2. So surface freezing almost all year round. And what I wanted to point out here is not only is it cold, but it is very saline water, and that is the water that is at depth, and that is the water that interacts with the ice. And when it does so, the very little heat content it has, it loses even more to interaction with the ice. And so it creates the coldest water on Earth. So it's very saline, and it's now the coldest water, and so it's the densest. And that's the abyssal water formation. So that's one process critical to the global thermodynamic circulation. The other process of interest to the global climate is the fact that these sectors that are highly melting, melting is basically injecting buoyancy because it's injecting fresh water into the system, and so it allows for this water that is sitting at depths to rise in the water column, and so either this water was highly productive or it had a high nutrient value to begin with, and it's being upwelled into the euphotic zone, so it creates an area for high productivity, or it picks up sediments as the glacier is grinding the seafloor and it comes out. So these regions are the most productive regions in the Southern Ocean. They contribute significantly to the carbon pump in the Southern Ocean as well. Okay. Now to ice-ocean interaction. So the thing that I'm interested in, I just wanted to cover very quickly the basic of the interaction. So you can think of the ice-ocean interface, and there is a boundary layer that interacts between the two. And so there is a heat and salt fluxes going into this boundary layer and then going into the ice. So we have heat fluxes in and out of this boundary layer that equal the melt, the loss of heat due to the melting. And for salt, we don't have any exchange of salt with the ice itself, but we do have one that which is due to the fact that water melts. Okay, and then at the boundary, what we have is we know that the temperature of the freezing temperature or the melting temperature, depending on which side of the curve you put yourself in, is not only dependent on salinity but also on pressure. So depending on how deep you are in the water column, you're going to be able to melt more or less. So that tells us exactly what temperature we are at the boundary. So these are the so-called three equation model. And from these three equations, you can then devise ways to infer in the model world, what kind of heat flux is going into this boundary layer, and once you know that, then you know what exchange you're supposed to expect in the model. And so these exchanges typically are modeled as an entrainment coefficient within this boundary, which is dependent on the velocity just below the boundary layer. And the basic idea of schematic is the following. We have an ice base, and we have some stationary ambient below that. It doesn't have to be stationary, but for this simple schematic it is. And then we start this stationary ambient is above freezing, so it starts to melt the ice. This melting put in some buoyancy, some fresh water into the system, making this turbulent plume rise following the ice base. As it does so, it entrains water within itself. And at some point, it becomes neutrally buoyant, and so it detrains the water column, which is not represented in this, or it doesn't, and it melts all the way through. At some point as well, it has lost all of its heat, and it starts, because the temperature of the water column determines the freezing point. You can have water that is stable in the liquid form, and as pressure diminishes, becomes frozen over, and that forms super cool water and fragile ice within the water column. So you can start to see inverted snow if you want. I have beautiful movies of that happening in the water column. So you see ice flakes, and then these ice flakes are burned, and so they start to rise up in the water column as snow falls down. And so of course this is a 2D view, but Earth is rotating, and if you have a cavity that's large enough, most of them are in the Antarctica, what you tend to see if you look towards a cavity is you will have this inflow of warm water and this outflow of relatively colder water induces a circulation in 2 dimensions. So you will tend to have in the southern hemisphere more inflow on the eastern side of the cavity and more outflow, return outflow on the western side of the cavity. And then of course, the system is much more complex than just having a cavity and a static ocean. What we have is we have sea ice, we have wind forcing, we have southern ocean and continental shelf interactions, and then we have a continental shelf interaction with the cavity. So it's a much more complex system to look at, and to do that we can use models to understand the system. We can also use a series of tools. So we have these three different scenarios. We have a scenario which is so-called mode 1, where we have basically water that's strongly interacting with the atmosphere above, so much so that it creates very salty water that dives all the way down to the water column, and so the water here has basically surface freezing temperature, and it's very salty, and that's the water that's the densest on the shelf, and that's the water that interacts with the ice, so it's very cold, and it creates ice shelf water that is very dense. That's kind of the Terra Nova Bay, Weddell Sea, Ross Sea scenario. And then we have, on the other extreme, we have the warm case scenario where the densest water is actually not that water doesn't exist. We have warm water here, and this warm water prevents sea ice to be strong enough to create this very dense water. And that's the water that interacts with the ice, and that creates a water mass that is buoyant, that also stratifies the water column. And then we have also intermediate systems where we don't have that much salinification rising from the surface, but we also don't have circumpolar deep water going into the shell, so it's kind of a mixed, basically just surface water, not very strong system. So if we concentrate then on the warm system, so it's basically a two-layer system, and the first time it was really well observed in Demons and Sea was in 1994. Stan Jacobs and Adrian Jenkins were on a cruise on the Palmer, and they did 3 CTD profiles in front of the Panama ice shelf. And these are the CTD profiles as temperature and as salinity. And what you have is really a two-layer system. You have cold water at the surface that interacts with the atmosphere, and below that you have modified circumpolar deep water that's warmer, it's about 1 degree at its warmest, compared to 2 degrees available offshore. So it's warm, but it's salty, so everything works out. It's still denser. And so that prompted a race to try to understand how this warm water would impact the ice. And so a few years later, Adrian got funded to deploy this Autosub 3 AUV under Panama ice shelf, and that's where I come in to use this AUV and analyze the observations from it. And so the first cruise that we did was in 2009, and in 2009 the weather was beautiful, it was warm, and we obtained 500 kilometers of observation beneath Panama ice shelf, so the ice is flowing in this direction, this is the ocean, and we launched the AUV in 6 different occasions, and it covered 500 kilometers beneath the ice shelf, so this is about 60 kilometers long, 30 kilometers wide ice shelf. And then in 2014 we did again different weather, but roughly the same success. So now we have 2 years of observations beneath the cavity, beneath that cavity. And we always had a lot of adventures with the AUV. It comes all the way back, and at some point it hit the ice, but still manages to survive. And sometimes you put a very expensive tool to measure turbulence at the front, and it turns out it's a very good bumper as well. Anyway, so these are nice stories from the field. So what kind of advance do you get in your understanding when you observe beneath an ice shelf? So what we know from satellite observation is the shape of the surface of the ice, and then we know from ship-based observation what the seabed looks like in front of the ice, and from radar, air-flown radar through the ice, we also know where the ice is grounded, what the seabed shape, well, it's actually the ice bed, but it's the same thing here, looks like. So you can infer, well, it's 1,000 kilometers deep here, a little bit deeper here, so let's put a slope in between the two, and maybe that works. That's what we thought we would see. Turned out, no, the system is obviously much more complex. Actually, in this particular system, what we found was a ridge, a transverse ridge, about 300 meters high, that was preventing the ingress of the warmest water all the way to the grounding line, and had a significant impact on the ice dynamics in the past, because the ice was pinned on it at some point.
Is that where the probe hit?
No,
Because it would have been funny if you
Yeah.
found the ridge by crashing into it.
funny isn't okay. That's an interesting way to phrase it. Well, we did hit interesting stuff, but it was the ice, ice base. So the seabed is kind of a strong reflector, and not. Okay, that's not a good way to phrase it. It's very easy to find a seabed with the instrument, with sound and everything. Other, like the ice, tend to be highly reflective on the contrary, and so they don't reverberate the energy, strongly back to you. And sometimes the robots don't see it very well. That and issues with software, which I won't go over. Okay, so this AUV is it's amazing because you can only go for 2 days at a time, but it has a very large payload, so it has a multi-beam that can map the seabed at meter scale resolution, all the ice space, and it can do observations of temperature, salinity, current, things like that. So this is features that were found on the seabed, in front or on top of this ridge. So actually, that's the top of the ridge. And what we found at the top of the ridge were these lineation features, which are reminiscent of ice flow. So as whenever ice is grinding on the seabed, it tends to leave linear features that go that are elongated in the direction of ice flow. And so that these are all of these lines that you see here, and basically they indicate that the ice was grounded in there at some point in the past. Since then we were able to drill through the ice, and James Smith was able to recover 2 meter sediment cores at 3 locations on this ridge, and using the dating of lead on the top of this cores, where you can see a clear transition between coarse sediment and thinner sediment, which arise from when you unground, or when you start to unground, you start to see this fine sediment piling up on top of the sediment. And so by dating this, we can actually have a history of the retreat. So at some point pre-1945, we were in a case where all of these were basically grounded, just started to unground at this location, in location B, and so by a 2D circulation route, the warm water was able to creep around and start to melt the inside of the cavity, but there was still the ice was still pinned on top of the ridge, and in the around 1970s, that was the last time that we saw it pinned on top of the ridge, and then since then it has retreated about 30 kilometers in now. So what we are looking at right now is really something that started to rise about a century ago, something like that, and had some, the geometry matters very much in terms of like dictating the rate of the retreat and everything. And of course, from this AUV observations, we also have a section of temperature, dissolved oxygen, water turbidity, and a quantity that I call meltwater fraction, which is basically if you assume that we have warm water, circumpolar deep water at the bottom, surface interaction, water that interact with the surface, the atmosphere here, and just ice. You have a 3 water mass system. You can infer how much meltwater is into the system, and we have it for 2 different years, going from the ice front, Calvin front, all the way to the grounding line, or pretty close to the grounding line. And so you tend to have always warm water at the bottom, and sometimes you have more warm water or less warm water. And so all of the low oxygen value indicate that these warm water are old water masses. They are water masses that actually arise from the Atlantic and spend a lot of time over the global ocean and then arrive here. And in 2014, as you can see, some of the surface water, which has a very high oxygen content, went into the cavity. We didn't see much traces of it in 2009. So the thermocline and the halocline go up and down with time, and that changes the properties of the water that go and melt the ice. And so in 2009, we had the shallower thermocline, higher heat content, lots of melt. 2014, deeper thermocline, less heat content, a little bit less melt. In terms of processes that arise when the ice melts, it's exactly the same schematic that I was showing earlier, where we do have warm water getting here, and then the meltwater, resulting meltwater is buoyant, and so it flows following the ice base, and as it comes out, it still has a significant amount of buoyancy, and we can dive into a little bit of the processes that arise when it comes out. So to look at that, we can forget about this, but we can look at the section that we did with, it's a high resolution section which had temperature, salinity, and turbulence in the water column. And so here we have temperature looking looking out from the cavity. So this is going to the north, and what you see is that this warm water here is coming back out in the form. It's slightly cooler because it lost some of its heat, but it's a warm signature compared to the cooler surroundings. And so you have these chimneys of warmer water that are coming out of the ice shelf, and it's localized in places. And whenever you have these chimneys, you tend to have a higher amount of turbulence in the water column. So this water is buoyant, it rises in the water column and trains mixes. What we found is that actually, as it does, just at the ice front, it reaches all the way to the surface, but actually a lot of the water, the meltwater, doesn't reach the surface and gets detrained laterally, mixed laterally before it reaches the surface, which is important because that indicates to the modelers, well, maybe some of this meltwater doesn't get injected here, it's actually injected here. That changes the properties in the water column in the middle, not at the top. And the reason it does that is because when you have a buoyant plume, if it's sufficiently large in scale, it starts to, it stretches the water column. The water column starts to become centrifugally unstable, and that leads to this lateral mixing. That's a nice paper by Alberto Navarro-Garbato a few years back. We can also look at the impact that geometry has on the circulation itself. Obviously, if you have a mountain, that restricts the water column thickness significantly, and so instead of having a nice direct link between what's going on here and what's going on in the back, what you have is actually a circulation like that, where you have this is warm water at the bottom, the color is the bottom, the temperature at the bottom of the water column, and the velocity at the bottom of the water column from observation in white and a model in black. Sorry. And what we see is we have warm water getting in from the eastern side of the cavity, but then that this circulation is cyclonic in an outer cavity, and it generates a jet at the top of the ridge right here, and there's another cyclonic circulation in the inner cavity. And because you concentrate a lot of the dynamics closer to the grounding line, you have a strong circulation, which maybe generates more melt than you would have otherwise. But at the same time, you also restrict the amount of heat reaching the grounding line. Instead of having the warmest water, you have water that's significantly cooler. That was in 2009. In 2012, we had a much shallower thermocline, a lower heat content, and as you can see here, maybe there's much less heat reaching the grounding line. So this is the anomalous heat, and so there's a 0.2 degree change at the grounding line, and the anomalous circulation is exactly the reverse of the mean circulation. Yes.
If you can make a statement about the exiting water, right?
Yes.
That has to be basically at the freezing point of that salinity water at that depth, right? So it's super cool.
No, because actually the system is not efficient. So
that was actually my question.
Right.
To what extent can you consider the system to be efficient, that all of the excess enthalpy that's coming in has been used to melt?
Right. So we know that it's not efficient,
Okay.
because we see there's a significant amount of heat still available in the water column as it comes out.
Okay.
But what I was saying earlier is that at the interface, that has to be true. It has to hold. But then in the integral, not all of the heat that enters the cavity is getting used to melt the ice.
Okay.
So it's circulating around. And
How efficient is it?
well, it varies from geometry to geometry, and that's the whole crux of future observations. And I go over that a little bit. But it is you want an efficiency number? I I don't have one.
10%.
It's a good question. No, it's tiny because melt is not that high. But, yeah, it's tiny. Right. So first part of the talk probably took much more time than I would have wanted it to, but so we have this cavity geometry, and within the cavity we have geometries that are very important for setting up the ice dynamics and the timescales of the retreat. And it also sets up, the ocean heat content, ocean circulation, how that impacts melt itself. So now in the second part of this talk, and I won't cover the third part, I'm going to look at the drivers of the heat content variability in the ocean, how that's linked to the climate system. And then I had a third part where I was also going to look at the spatial variability that needed to be covered if one wanted to model these systems. Turns out all of the action occurs in very restricted areas, small areas, and so it's very difficult to look at these questions of efficiencies and coupled dynamics without actually resolving these tiny scales. I mean, you have to parameterize them, and that's the goal of the game right now, is to try to parameterize these small systems into bigger models. So what we know about temporal variability in these systems from observations is, well, we have summer observations going back since 1994. It's sporadic, but it exists. So in front of Pannon Glacier, in this paper, I had 5 observations. So these are sections of temperature in front of Pannon Glacier, looking out from the ice shelf. So there's always warm water depths and cold water on top, but we have thicker or thinner warm water layers going on with time. And we can also look at the circulation going in and out. So here in is red. Actually no, in is blue. So actually we're looking into the cavities. I'm sorry. And so in is blue. So it's coming in into this sector and it's coming out at shallower depths on the western side of the cavities all the time. But so we have some variability from these inversion of temperature, salinity, dissolved oxygen, and fluxes in and out of the cavity. We can actually infer how much melt occurred if we assume a steady state. And so these are the numbers that we obtained, going from 50 cubic kilometer per year in 1994 to 80 in 2009, and then way back down to 40 in 2012, and a little bit back up in 2014. So that's for Pannon and Glacier. We can do the same game also for Getz, where we only have 2 years, but same kind of indication. Early 2000, low, and then increase in the late 2000s. And actually the best record we have is for the Getz ice shelf. So I just showed you Pineland and then Getz, and so that's Dodson now. And Dodson ice shelf was, in this paper, we had 8 years of observations, and here is the record. The black curve shows the meltwater flux in gigaton per year, and the red curve shows the temperature, the heat content average over the water column in front of the ice. So we have years here, sections where we have high heat content, thick warm layer. We have years where we have a thin warm layer, and we have this roughly decadal cycle in the heat content, where we had a low heat content in 2000, higher heat content late 2000, and then a big drop, and then maybe the beginning of a recovery, but not that much here. What we can also look at here, because we have more points, is the relationship between, comes up to the efficiency of melt, the relationship between melt and temperature available. And so that's this curve here, and so it's not a linear curve, it's a roughly quadratic curve, which shows that basically melt is highly sensitive to temperature in this range. If you go into the low heat content range, there's not a lot of sensitivity to changes in temperature, but as you go up, if you just increase the temperature a little bit, you're going to have a very strong response in terms of melt. The ice responds to this forcing, and the indication that we'll go over here is that we have from Pine Island Glacier, where we had a mooring time series in blue of ocean heat content. It's a 6-year record here of ocean heat content. So it's basically warm, and then in 2011 there's a big dip. In 2012 it's an even bigger dip, and the ice responded during that time because it was kind of calm for ice dynamics during that time, and so we were able to see that with roughly a 6 months delay. There is a decrease in the ice velocity that responds to the cooling of the ocean. We can also look at the same thing for Dodson, where we have this decadal time series, decadal variability, and what we see is also bounding line advancing or retreating depending on the ocean heat content. Okay, so glacier dynamics is sensitive to this oceanic melt and its variability. Now, what drives this variability is another interesting thing, and that's the last thing I will cover, I think. So here is the map of the ocean heat content. Well, it's actually temperature above freezing at 400 meters in a model, but this model represents the observation relatively well. And so this is the MNCZ, that's Pine Island, that's Dodson, that's Guest I was telling you earlier. And what we have is that offshore in the Southern Ocean we have this pool of warm water, circumpolar deep water below the surface. And all along the continental shelf in Antarctica there is a slope current, which is its position is dictated by the fact that there is a break in the continental shelf geometry. And this slope current it basically induces a geostrophic shear in the water column, and depending on the barotropic component of this of the current, it can either lead to a strong surface flow in the westward direction and zero flow in the eastward direction at the bottom, or a zero flow at the surface and an undercurrent that goes along the shelf edge going in this direction. In general, in Antarctica, what we have is a strong westward flow at the surface. In this region, that's not the case. That's mostly wind driven. What we have instead is an undercurrent that goes along the shelf edge that advects water and retroflects into glacially carved troughs. And so it basically feeds these troughs with warm water at depth. So from simulations, what we infer is that modulating the intensity of these jets is it's the lead source for modulating the amount of heat that gets onto the continental shelf. So this is really the gateway, measure gateway. Anything that happens on the shelf is actually removes heat from the system. Either you lose it to the atmosphere or you lose it to ice melt. Okay, so what drives this undercurrent? The strength of this undercurrent. It looks like it's actually the wind on top of it, the zonal wind on top of it. What did I want to show here? I don't know. So the wind, this is the wind, this is the climatological wind structure over the Amundsen area. And so what we have over the Amundsen is, and this is the shelf break, the black line here. And in general, the shelf break in most Antarctic setting is actually close to the calving front, and you have the calabatics coming out from the ice shelf, projecting westward. But here it's sufficiently offshore that it actually lies into this null between the eastward, the westward flowing calabatics and the westerlies northward. So it's in this strong curl area. And so if you look at the zonal wind within this box and you look at it in era interim, this is the time series that you have. So it's centered on zero, so zero mean, and it has some strong decadal variability. If you take this same time series and you correlate it with sea surface temperature in color and sea level pressure in contours, what you find is this very nice pattern of warm, cold, warm, or it's actually positive, negative, positive correlations. And this patch is actually very strongly reminiscent to that of El Nino or the IPO or any type of index that arises from convection anomaly in the tropical Pacific. So you can actually.
So what's the geographical scope of this?
So.
No idea.
Oh, you don't. Yeah, you don't see. So this is the whole globe.
Oh, okay. That was totally unclear.
Right. It's actually much better on the screen.
Oh, you should be. Oh, you can't use the.
Yeah.
So the yellow is messed up.
Okay, so that's the American continent.
Okay.
That's Australia. This is the Pacific, and Antarctica is here. And yeah, that's not very good. What can be done? What we can do as well is just correlate this the wind, this time series with all of the indices, climate indices that exist. And what we find is that we have a very strong correlation with the Southern Oscillation Index, the NEO 3.4, the PDO, the IPO, and anything else doesn't match very well. So SAM, Antarctic Oscillation, AMO, things like that. Right, what do you have here? And actually, if I superimpose, I don't know if you can see anything here, but if I actually superimpose the IPO or the SOI on this time series, it's actually very difficult to see any difference. So that's why there is a very strong connection, very good correlation between the two. And the reason for that is actually pretty simple. There's a direct connection, atmospheric bridge. Whenever there's an atmospheric convection anomaly arising from tropical Pacific, it radiates waves forward, and the area that is being touched by this forward radiation of waves in Antarctica is exactly the Amundsen Sea. So this is the center for all of this variability. Okay, so we can actually use this link to then try to go back in the past and infer what was going on in terms of wind variability over the last century. Because if we know what the variability of the wind has been, maybe we know what the variability of the undercurrent has been, hence the variability of the heat content on the shelf, hence the melt, hence the ice dynamics. And so to do that, what can be done is if you are to use a model to hindcast what happened over the last 100 years, models don't have the right phasing or even modulation of El Nino or tropical Pacific convections, just because it's a very chaotic system to model. But what you can do is you can force the model to represent the tropical Pacific exactly, because we have observation of the SST since 1920s. And so that's what's done in this space experiment. So you force the model to have exactly the SST in tropical Pacific, and when you do that, you force the model to radiate these forward waves and to match the phasing of the variability that should have occurred in the Amundsen Sea. And so here what I'm showing is the PACE ensembles. So it's a 20-member ensemble going back to 1920, and so that's the black curve. Overlaid on that is the era interim for the era interim period. And so you can see that the PACE ensemble in era interim have a nice correspondence. You wouldn't get at all the same correspondence if you use Lance or any other kind of ensemble. And that's because most of this variability is indeed driven by the tropical Pacific. So if you represent tropical Pacific convection properly, you can represent the atmospheric wave train and the variability in the Amundsen Sea. Okay. But what you can also see in this time series is that overlaid on this decadal variability, there is a trend in the zonal wind, and that's interesting, right? Because not only do we see decadal variability, which would lead to more heat or less heat going onto the shelf, but if we have a trend, and that trend is going in the direction of increasing undercurrent strength, increasing heat content going from the Southern Ocean onto the shelf, that could explain the trend that we've been seeing in the axe. And so actually this trend is very reminiscent, it's very similar to that you can see in any ensemble that have been run to date. So this is the trend that you have in the Lance ensemble. So obviously there's no decadal variability, because by definition this has been smoothed out. but you have the same trend, and this trend is that due to anthropogenic radiative forcing. There is a little bit of an ozone component as well, but it's actually smoothed out over this centennial timescale. Well, it's because it actually goes against the CO2 component. I'm happy to talk about it. Yes.
Okay,
Yes.
why would the ozone cancel out over a century period? Like
No.
it starts in like 1983 and then becomes
Yes.
much stronger, and then kind of flattens out in the last 10 years.
Yes.
Right. But why
So
would that
so we
be?
shouldn't. What my point was that we shouldn't have much of it here.
Right.
That was my main point. But it definitely should have an impact over this.
Yes, but I'm
area.
not seeing anything that resembles
Right.
the response.
That's
to an
true.
ozone hole.
Because most of the thing that you should see here is actually the decadal variability, and maybe there's an impact over this time period, but it's difficult to see. When you talk about the centennial trend, a trend over 30 years is I don't know if we can decompose this.
I mean, if you
100
looked
year.
at the zonal mean winds in a model that has an ozone hole, you will clearly see the impact of the.
Right. So it does
Right.
have, it must have an impact here.
Right. I mean, it could be that you're just looking at a small part.
Yeah.
And it's just not very important there.
Yeah.
So that could be the case. But
Yeah.
it's not that it's been averaged out by the trend.
No, so I misspoke. What I meant is it doesn't really matter for the point
Okay,
I was
well,
making.
that's fair.
What can be done as well here is if you just want to look what is the tropical component of this variability, you can actually remove that trend to the pace response. That's what we have here, and what you can see is that the decadal variability has not really changed in nature over the course of this century, if you believe that. That's not exactly true actually, but so that first there's no trend in the tropical response. The first
You've
point.
taken out the trend, so
I've taken out that trend, the one that's due to anthropogenic forcing. But you could argue maybe there's a tropical, the one that just arises from natural variability, and we don't see any of that. Right. So what is what's the structure of the trend? That's the structure of the trend in the zonal wind, and so it's an increase of the westerlies in the Southern Ocean and a southward shift of the westerlies. Right, and so now that we think that we have a time series that maybe represents the past, how does it match what we know about the past? And so here I'm showing the time series, the same time series, but what do we know about the past? Well, we know that starting in the 1940s, we had a little bit of an ungrounding, and then in the 1970s, another significant ungrounding of Panyan Glacier. And interestingly enough, actually very weirdly enough, I would say, on this trend, what you can see is that maybe at the beginning of the century, the decadal variability wasn't strong enough to induce a lot of large heat flux flow that would on the continental shelf that would then impact melt. But in the 40s, there was an event that was stronger than all of its predecessor, and that may have led to the starting of the ungrounding of Panyan Glacier. And then the trend continues. It's a small trend, but as time goes on, the decadal variability starts to have more and more positive impact, more and more impact on the melt. And so in the 1970s, there was another event, and then so that's two good matching timescales. What we can do as well is then look at the velocity response of the ice since the 1970s. Actually, if you just with your eye, you can look at, for example, Panyan Glacier started, accelerated from the 70s to the late mid 80s, and then slowly, there was kind of a small deceleration or flattening out of the acceleration, both for Panyan and Ainswaits during this time period, and that's a period that corresponded to a dip in the heat content. And then we had an increase in the heat content, and both glaciers started to accelerate. And then maybe here there's a flattening out weights, not so much for Pine Island, and then another acceleration. Here, not much change apart from this part of the record for Pine Island, where there was a dip in the heat content and a deceleration of Pine Island. So every glacier has its own geometry, its own dynamics, is going to react differently to the forcing, but the fact that we had a consistent response is actually indicative of a link between the two, or it's actually not discounting it.
Where's the 98?
Let's see here. See here.
Where's the 98?
98. Yes. Well, it's here. Yeah. Yeah.
So 1940 is massive on the yoga, right? 1941, 42.
Yes.
And you can see that in the readings as a positive.
Yes.
Right.
Right.
And
So
and you had a really good relationship to ENSO.
Yes.
In the other one, but
Yes.
it was reversed. Right. So the ENSO correlation in the latter part of your thing is opposite.
Well, so remember that 98 is a strong La Nina. So 97 is a
Well,
strong
97,
La Nina.
98.
Right. But then there's a strong La Nina that follows it.
Mm-hmm.
So if you average that over a decadal
Is this
temperature,
average or is this?
it's
year by year?
that's 2 year average. That's 2 year running window. Both the El Nino and the zonal wind match actually very well over this time period.
Right.
Yeah.
But the
Well-
sign of the correlation is that positive El Nino even averaged over 2 years.
But
is-
negative La Nina
is
goes the other
so
direction.
when you're applying the Southern Oscillation Index,
Yeah.
Southern Oscillation Index is down when ENSO is up, right?
Yes. Right.
So and you had
But the
so it's a
correlation is-
positive correlation with SOI,
Yes.
which means that it's a negative correlation to El Nino 3.4,
Yes.
right?
Yes.
And yet the anomaly in the 1940s was a very positive Nino 3.4.
Right.
Right. So
okay.
so is there a possibility that the silent response is shifting?
Not when you look at the time series 1-to-1. I'm happy to do that with you. But remember it's a correlation,
Mhm.
and it's a correlation that holds at decadal, actually multi-decadal time scale. So La Nina is going also have an impact as well as much as the El Nino, and so at decadal time scales, I don't know what the impact of the 97 El Nino had at decadal when I average it out. And so maybe to finish, I'll go over future scenarios. So using so the pace ensemble ends in 2015, I think. But then we can look at the lens ensemble to look at what should we expect over the next century in terms of this trend, and depending on which scenario. So the RCP 8.5 scenario continues on the same trend over the next century, and so in terms of melt, what you may expect is that this decadal variability started at the beginning of the 19th century or 20th century with not having a lot of impact on the melt. Now there's a zero mean, so it has a lot of impact on the melt, and maybe by the end of this century we will be in a regime where there's always warm water, and this system will be very inefficient. It will be melting like crazy. Or if we are on the RCP 4.5 scenario, it will actually still have a positive trend, but it's much weaker. It's actually not significantly positive, and so maybe we stay in the same regime where we have a lot of decadal variability and close to zero average. And so it all depends on what the anthropogenic forcing will be. Right, so I've talked about the impact, the connection between the heat content and the wind forcing and the tropical Pacific variability and the anthropogenic forcing going into the future. And I think it would be wise for me, if we don't want to go into the 2 hours mark, to stop here. And you have a question?
So when you were showing pictures of the wind fields, you said that right now you're in this sweet spot, like between the easterlies and the westerlies.
Yes.
So the catabatics and
Yep.
So it seems like you're shifting between regimes. So do you have scenarios like if that like the connectedness would change very much then depending on how much the grounding line changes. So shouldn't you have like alternate scenarios based on where the grounding line is and use those in conjunction with your RCPs?
Yeah. You definitely, I mean, the best, a centennial timescale is not going to change significantly enough that, that won't be a problem. At millennial timescale for sure, you know, the ice front and all of the ice dynamics will be definitely at a much different point. I would expect though that the shelf break dynamics, the shelf break is not going to change. And so
But the break's location
the break location is not
the
going to
easterly
right.
and the
So what may
westerlies
change
and Tibetics.
what may change is the position of the westerlies. They may shift south or I don't know, go back north, and that would have an impact on. That's basically what the trend. The trend is a reflection of the southward shift of the westerlies. If that trend continues, that's always going to increase the eastward barotropic component of the flow at the continental shelf break, which is going to lead to more influx, so a stronger undercurrent and more influx going from the Southern Ocean onto the continental shelf. One thing that could happen, as the system retreats all the way back, is that the heat that's coming onto the shelf is now it's interacting also with the atmosphere above and sea ice formation. And if we have a shelf that's wide enough, then you're in a scenario like the Ross Sea, where actually most of this heat is being removed, used up by the atmosphere and the sea ice, and actually now the heat content available to melt the ice sheet is very small. But we're not in this scenario yet. That's a good question. Any other question? I think it's a good point to end the talk.
I was going to ask you, is there any evidence of change in the decadal variability over time? Like
There is. So if you believe the reconstruction, the centennial reconstruction of SST and the representation of the decadal variability or internal variability within it, there is a little bit of a change. It's been looked at by many people. The amplitude seemed to have increased a little bit. So you could argue that maybe what we are looking at on top of the trend is an increase in the amplitude of this variability, which would lead to big changes in the heat content, larger changes in the heat content, and given that the ice response is strongly nonlinear, it will respond much more strongly to an increase in heat content than a decrease in heat content. Then maybe that could have led also to the instability that we are looking at right now.
So in the PACE simulations, is that increase in decadal variance coming from the ENSO region itself, or is it the expression of the same variance in ENSO, but it's being increased because of the trend in the westerlies in your particular
That's
location?
a very good question. Very good question. And I don't know. I don't know the answer to that question. So I have some hints of response. I'm a answer of the proof, but I'm not a specialist. So one issue with the model representation of ENSO and its variability and everything and trends within it is linked to a poor representation of the tropical cold tone. And there's a few papers that came out recently that looked at simpler models of ENSO, which do better or not as good a job, depending on. and they would tend to show a trend arising from the tropical Pacific that goes in the other direction than that is modeled in the Earth system models. So if that's true, maybe there's a trend originating from the tropical Pacific that goes more into a La Nina condition that would counteract the trend that arises from the westerlies. I don't think we have a good handle on that. There's a lot of work needs to be done. Yeah, and I don't know how they try to find out. Yeah.
Is the freshwater input small enough rates that it basically gets diluted quickly enough that it doesn't impact the dynamics much?
Looks like it has a very strong impact on the dynamics. So it does in Earth system models, but then Earth system models are coarse, and you could say, well, you know, they don't represent gravity well. It also does in very high resolution Amundsen-C, so kilometer resolution model, and it does in very, very fine. So basically, everything driving the dynamics in continental shelves in polar regions is the salinity. And so if you put iceberg melt, you know, at the surface or in the middle of the water column, or you put ice shelf melt in the middle of the water column, it changes it changes everything. It changes sea ice formation processes, and so basically it changes all of the efficiencies in the system. The efficiency within which the heat content is being used for melting the ice, the efficiency within which heat content is being used to reduce sea ice formation, and everything. So yeah, it's
So it's that absolutely
important.
affecting the local heat budgets, but is it affecting the current structure?
yes, it affects the current structure as well. I mean, it must. Although I don't. Yeah, it must affect the current as well. And it certainly affects also deep water formation, global thermal circulations, things like that.
Do we have any questions from those listening outside on the WebEx?
Does this red mean it's been muted the whole time?
I think the red means it's recording, doesn't it?
No, that red means it's muted.
Oh, when you turn it on, you press the.
Yeah, but like if you're
That's
no,
red.
that's muted.
Oh, it's been off.
Didn't somebody complain?
No one complained.
No,
I
because
asked.
Craig muted them.
Well, it could,
I asked
it
on.
could be that your microphone is picking up, like somebody's microphone is picking up the sound.
Maybe.
But the telecon, there's no sound going out of that telecon.
There were three people.
So
There's
must
now
be
now
something.
one person.
Okay.
So there must be some audio going on.
Okay. Yeah, you don't want to check.
They don't react now.
It's too late.
Too late now. Yeah. You need to check these things. They can always
Red
watch.
means
Make it-
bad.
I thought
Okay.
red
red
means that it's recorded.
Red means
One
it's
of
muted.
the photos you get the
Red
markers.
doesn't work.
It's mute. See? Unmute. Alright, never mind.
So you're recording with audio from this as well?
Yes.
Okay.
So the audio on the record. We'll work it out. Do you know how many times it took us to fly
Yeah,
something to be
Oh, there's been a lot of people.
Slightly more complex, but okay, fair enough.
Well, you know what? You see what they actually flew? The answer is no. It's actually much less complex.
So we get all the bugs out of our GCM.
And then we put in some more.